Hey everybody, this is example number 1 for structural dynamics to response to harmonic excitations. The problem statement that we have is the undamped spring mass system shown in the figure below has the following properties. The mass is equal to 5 kilograms. The spring stiffness is equal to 5 newtons per millimeter. The mass has an initial displacement of 10 millimeters and an initial velocity of 150 millimeters per second. And it's excited by a harmonic force with the following characteristics. The harmonic force has an amplitude equal to 100 newtons, and the excitation frequency is equal to 20 radians per second. And we need to find the frequency ratio, the amplitude of the force response, the displacement of the mass at time t equals 2 seconds, and the velocity of the mass at time t equals 4 seconds. So here's our figure of our undamped spring mass system. We have the spring over here, the mass, and the harmonic force function is given by F sub O, Fo times sine of omega t, capital omega t. And F sub O, Fo is the force amplitude, and omega, capital omega, this is Fo, and capital omega is the frequency of this forcing function. And we were given both of these values. This is 100, and the frequency, excitation frequency, is equal to 20 radians per second. Before we proceed with the solution, I just want to let you guys know that this example is brought to you by Bentley. And Bentley Systems is a software development company that supports the professional needs of engineers, designers, planners, and contractors responsible for creating and managing infrastructure. Bentley has tailored software applications for design, modeling, and analysis of buildings, structures, bridges, plants, and more. I have used Bentley software, and I can say that the software was very easy to use, and the support that came with it was impeccable. Whenever I needed help, the Bentley team was there for me. And here's their website, Bentley.com. There's a link to Bentley.com and some of their YouTube channels within the description part of this video. So if you're a student and want to get familiar with the software and get a leg up over your colleagues during your job search, academic licensing is available through Bentley. And if you're a practicing engineer and you want to sharpen up your skills, they have a bunch of videos and webinars on their website as well as their various YouTube channels. So please check them out. And now coming back to our example problem, the first step will be to calculate the natural circular frequency of the system, of the spring mass system, and that's equal to the square root of the stiffness divided by the mass. So that comes out to be 31.62 radians per second. Next, we can calculate the frequency ratio, and the frequency ratio is equal to the frequency of the forcing function divided by the natural circular frequency of the spring mass system. So it's capital omega divided by lowercase omega, and capital omega is the excitation frequency, the frequency of the forcing function, and lowercase omega, which we just calculated, is equal to the circular natural frequency of the spring mass system. So we plug in the numbers, 20 divided by 31.62. So our frequency ratio is equal to 0.633. After this, we can calculate the amplitude of the force response. And the formula for this is equal to the amplitude of the forcing function divided by the spring stiffness, and this total quantity divided by 1 minus r squared, 1 minus the frequency ratio squared. So the amplitude of the forcing function is equal to 100. The spring stiffness is equal to 5 divided by 1 minus 0.633 squared, the frequency ratio squared. So the amplitude of the force response is equal to 33.37 millimeters. Once we've calculated this, now we need to develop some type of expression, a displacement expression for the mass. So here's a mathematical general solution, the general expression for our case. In our case is for forced harmonic response of an undamped system. So it's equal to, the displacement of the mass is equal to A times sine of lowercase omega times t, plus B times cosine of lowercase omega times t, plus the amplitude of the forcing function divided by the spring stiffness, all divided by 1 minus r squared, times sine of capital omega times t. And this value over here, we just calculated it, and we called it x sub f, the amplitude of the force response. So based on this expression, we know everything except A and B, and we need to solve for A and B based on the initial conditions, based on the initial displacement and initial velocity. So we just further simplified this expression by plugging in the values that we actually know. So it's A times sine of lowercase omega, which we calculated 31.62 times t, plus B times cosine of 31.62 times t, plus 33.37, which is x sub f, times sine of omega t, capital omega t. Capital omega is equal to 20 radians per second. And we also write the expression for the velocity. So we take the first derivative of the displacement, and we get 31.62 times A times cosine of 31.62 t minus 31.62 times B times sine of 31.62 t plus 667.4 times cosine of 20t. So we have an expression for the displacement and the velocity, and we have to solve for A and B. So let's first take a look at the condition of initial displacement at time t equals 0. So at time t equals 0, we were told that the initial displacement is equal to 10 millimeters. So we plug in t equals 0 in the displacement function, and we get A times sine of 0 plus B times cosine of 0 plus 33.37 times sine of 0. So all the sine terms, this will go to 0, this will go to 0. So we're left with B times cosine of 0, and cosine of 0 is equal to 1. So we're left with 10 equals B. So now that we solve for B, we still need to solve for A. So we're going to use a second initial condition, and that's based on the initial velocity. And we were told that the initial velocity at time t equals 0 is equal to 150 millimeters per second. So we plug in t equals 0 into the velocity function, and we get that 31.62 times A times cosine 0 minus 31.62 times B times sine of 0 plus 667.4 times cosine of 0. So the sine term, the sine of 0 will go to 0. And the cosine of 0 is equal to 1 here and here. So our expression simplifies to 150 equals 31.62 times A plus 667.4. So we rearrange this equation and solve for A, and A equals negative 16.36. So now that we know both A and B, we can write a complete equation for the displacement of the mass and the velocity. And here it is. So this is for our displacement, and this is the velocity. And here's what we had for A and B here. A, B. So now we can calculate the displacement or velocity of the mass at a given point in time. So the problem asks us to find the displacement at t equals 2 seconds. So we plug in t equals 2 seconds into this displacement function here. and we find that the displacement is equal to, so this is after I plugged in the numbers. I got negative 6.49 plus 9.18 plus 24.86. Those are based on the three terms in the displacement expression. And so the displacement at t equals 2 seconds is equal to 27.55 millimeters. And lastly, we can calculate the velocity at time t equals 4 seconds. So we just plug in t equals 4 seconds into this velocity function here. And we get that it's equal to negative 354.31 minus 230.39 minus 73.67. So the velocity at time t equals 4 seconds is equal to negative 658.37 millimeters per second. And this is the end of this example. Please subscribe to the channel. Like our Facebook page. It's facebook.com/engineeringexamples. And also visit our website and sign up for our email list, where you can stay up to date on the latest engineering content that we're producing at EngineeringExamples.net. Thanks.